Right now, as you sit here, the Earth is spinning at over 600 kilometers per hour. At the same time, it's racing around the Sun at 30 kilometers per second. But the Sun itself isn't fixed either. It's hurtling through the Milky Way at 230 kilometers per second, and our entire galaxy is orbiting the center of a massive cluster of galaxies, all of them spinning together like gears in a cosmic machine. Every planet turns, every star rotates, every galaxy spirals. Even the smallest particles, electrons, protons, quarks, carry their own intrinsic spin. From the tiniest atom to the grandest supercluster, rotation is everywhere. But why? Why does everything from dust to galaxies spin? What started it all? Was this cosmic rotation built into the very birth of the universe itself? If we could rewind time to the first instant after the Big Bang, would we find a spark of motion already there? A twist written into the fabric of space from the very beginning. Today we'll uncover how this invisible force rotation shaped everything we know. The orbits of planets, the birth of stars, the stability of galaxies, and even the magnetic fields that protect life on Earth. This is not just about motion. It's about one of the most fundamental and mysterious patterns in nature, because the universe doesn't drift quietly through space. It spins. Right now you're moving, even if you think you're sitting perfectly still. Look around. The room seems quiet, unmoving, but beneath you the Earth is spinning once every 24 hours, turning eastward at 674 kilometers per hour at the equator. That means that in the time you've taken a single breath, you've already travelled nearly half a kilometre through space without even realising it. The moon doesn't stay put either. It orbits Earth once every 27 days, moving at 3,600 kilometers per hour, locked in a gravitational dance that has lasted for billions of years. Together, Earth and Moon revolve around the Sun, racing through the solar system at nearly 30 kilometers per second, fast enough to cross the entire diameter of Earth in less than 7 minutes. But even the Sun is far from stationary. Our star is one of hundreds of billions orbiting the center of the Milky Way galaxy. It completes one full revolution every 230 million years, traveling at 828,000 kilometers per hour. And the Milky Way itself isn't resting either. It's being pulled toward a massive region of space called the Great Attractor, a gravitational center surrounded by thousands of other galaxies all moving together through an invisible current of cosmic gravity. When you look up at the night sky, you might think the stars are fixed, scattered on a static dome, but every one of them is moving, some faster than bullets, some slower than glaciers, their paths twisting and intersecting across millions of years. Even the constellations we know today are only temporary. In a few 100,000 years, Orion, the Big Dipper, and every familiar pattern will be gone. Their stars dispersed across the galaxy's endless spin. And beyond our galaxy, there's more. The local group, a cluster of more than 50 galaxies, is itself rotating and drifting toward the Virgo supercluster, a massive structure that spans over 100 million light-years. And all of this, every star, every planet, every galaxy, is part of an even greater system. A cosmic web still expanding, still in motion since the moment of the Big Bang. So when we say our world is spinning, we're not exaggerating. We are passengers on a moving planet orbiting a moving star inside a moving galaxy, racing through an ever-spinning universe that has never stopped turning. It's a humbling thought that even when we're standing still, we're already travelling faster than we can possibly imagine. Motion is not the exception. It's the default state of existence. We've seen that everything moves from our spinning Earth to the vast galaxies drifting through space. But have you ever wondered why they spin at all? Why doesn't a planet just form perfectly still? Why can't a cloud of gas collapse into a quiet, motionless ball? The answer lies in one of the universe's simplest rules. Motion never disappears, it only changes form. When a giant cloud of gas and dust begins to collapse under gravity, it's never perfectly uniform. There are always tiny differences, one side a bit denser, another slightly faster. Those small variations are enough to create a gentle twist. And as the cloud shrinks, that twist grows stronger. Just like a skater spinning faster when pulling her arms in, the collapsing cloud speeds up as its radius gets smaller. That's how stars and planets are born, not in stillness, but in motion. This is the power of angular momentum, the cosmic law that keeps rotation alive. It's not something added later. It's something inherited from the moment matter begins to move. Once rotation begins, it resists change. There's no air in space to slow it down, no friction to stop it. So the motion continues preserved for billions of years. Even the solar system we live in is a relic of that process. 4.5 billion years ago, it was just a swirling disk of gas. At its center, gravity pulled the densest region inward. That became the sun. The leftover material flattened into a rotating ring. And from that ring, the planets were born. Each planet kept its share of the original spin. That's why most of them orbit in the same direction, and rotate along nearly the same plane. This solar system is literally the fossilized memory of a cosmic rotation, but not everything spins the same way. Some planets tilt, some even roll sideways. Uranus, for example, spins almost on its side, probably because a massive collision long ago knocked it over. Venus spins backwards compared to most planets, a sign that violent impacts or tidal forces once rewrote its motion. Yet even those chaotic events never erased angular momentum. They simply redirected it. Rotation isn't just common, it's inevitable. Anytime gravity gathers matter, rotation naturally emerges. The only way to stop it would be to perfectly balance every motion in every direction. Something nature has never done, not even once. So from the smallest dust grain to the grandest galaxy, spin isn't an accident of physics. It's a built-in feature of how the universe organizes itself. The cosmos doesn't need a reason to spin. Spinning is the reason things exist the way they do. Once something starts to spin, it changes everything. Rotation isn't just a background detail. It decides how things look, behave, and even survive in the universe. Spin is one of the most creative forces in nature. Let's start small. When a forming star begins to rotate, that motion keeps it from collapsing completely under gravity. Without spin, gravity would crush everything inward until it became a single point. But rotation creates a delicate balance, a kind of invisible support. It flattens the gas into a disk around the newborn star, and that disk becomes the birthplace of planets, moons, and asteroids. So spin doesn't just stabilize stars, it literally builds solar systems. The same rule shapes the planets themselves. Earth, for example, bulges slightly at the equator, about 43 kilometers wider there than from pole to pole. That's what happens when a planet spins at more than 1/600 kilometers per hour. Centrifugal force pushes outwards, competing with gravity's inward pull. Without that balance, Earth's surface and maybe even its climate would be very different. Spin also controls how planets live and die. Fast-spinning worlds have powerful magnetic fields, created by the motion of molten metal deep inside their cores. That magnetic field shields us from deadly solar radiation. It's one reason life on Earth can exist. Mars, by contrast, spins more slowly and lost much of its internal heat early on. Its magnetic field faded and the solar wind stripped away its atmosphere. Two planets, same star, but rotation decided their fate. Now scale that up. Stars too are shaped by their spin. A slow-spinning star burns steadily for billions of years, while a rapidly spinning one becomes turbulent and unstable. When it runs out of fuel, that spin can tear it apart, collapsing it into one of the most extreme objects in the cosmos, a neutron star. These stellar corpses spin hundreds of times per second, firing jets of energy that sweep through space like lighthouse beams. We call them pulsars, and they're some of the most precise clocks in the universe. Their rotation is so stable that scientists use them to measure time itself, and when rotation reaches its absolute limit, when gravity overwhelms even that, we get the most mysterious structure of all, the black hole. A black hole doesn't just pull things inward, Its spin twists space and time itself, dragging everything nearby into a swirling spiral known as frame dragging. In those regions, even light can't escape. It's the ultimate example of motion shaping reality. Spin builds stars, it protects planets, it sculpts galaxies and even warps space-time. Every structure we see, every elegant curve of a spiral galaxy, every stable orbit, every shimmering ring, is the result of billions of years of spinning matter finding its balance. When we talk about the beauty of the universe, we're really talking about the art of rotation. The cosmos isn't still because stillness would mean collapse. Instead, it dances every atom, every planet, every star, locked in a rhythm of endless motion, and we're part of that dance, riding on a spinning world, circling a spinning star, inside a spinning galaxy, in a universe that might itself be turning. Everything that spins, spins for a reason. The universe doesn't waste motion, it follows rules. Invisible, unbreakable, and astonishingly simple. The first is inertia, the tendency of any object to keep doing what it's doing. If it's still, it stays still. If it's moving, it keeps moving unless something stops it. That's why a spacecraft launched into orbit can circle Earth for decades, gliding endlessly through space with no engine, no fuel, no resistance. In the vacuum of the cosmos, there's nothing to slow it down. Motion once begun simply continues. Then comes gravity, the quiet architect of everything that spins. Gravity doesn't just pull straight inward, it curves motion into orbits. When a planet falls toward a star, it doesn't crash head-on. Its sideways velocity bends that fall into a loop. That's why we orbit instead of collide. It's a constant tug-of-war between falling and flying away. The result? The graceful balance we call an orbit. But the rule that keeps the universe in perfect rhythm is the conservation of angular momentum. It means that the total amount of spin in a system can never be created or destroyed, only passed around. A figure skater, a collapsing star, or a whirling galaxy all obey the same law. If something shrinks, it spins faster. If it expands, it slows down. The numbers always balance. This single principle links the smallest and the largest scales of existence. The same physics that governs the spin of an electron also governs the dance of planets and the swirl of galaxies. It's one universal language of motion. Even collisions don't break the rule, they just redistribute momentum when galaxies crash together. Their stars rarely collide directly, but their angular momentum blends, forming new shapes, vast elliptical giants, each one still spinning, still conserving motion. Every spin in the universe is a kind of inheritance, a gift passed down from one era of matter to the next, from the first atomic particles to the galaxies that light up the sky. Nothing is wasted, nothing stops. Momentum simply changes form, from the swirl of a collapsing cloud to the spin of a planet, from the dance of a planet to the orbit of a star, from the spin of a star to the spiral of a galaxy. That's why after 8 billion years, the universe is still turning, the same motion that began in the beginning. The same subtle imbalance that started everything is still echoing today. Every planet's day, every galaxy's rotation is a trace of that first movement. We live in a cosmos that remembers. It doesn't forget motion, it keeps it, transforms it, recycles it. Like a cosmic engine that never switches off. It turns endlessly powered not by mystery but by the elegance of physics. Spin brings order to the universe, but it also brings chaos. The same forces that shape stars and planets can just as easily tear them apart, because motion in space is never perfectly balanced. Every collision, every uneven pull of gravity creates tiny imperfections, and over billions of years those imperfections grow into drama. Take Saturn's rings. At first glance they look peaceful, thin, shimmering bands of ice and rock, circling in perfect harmony, but look closer and you'll see turbulence everywhere. Each piece of debris follows its own path, nudged by the gravity of nearby moons. Some chunks are drawn together, others are flung apart. The result is a masterpiece of balance born from chaos, a frozen storm of billions of fragments, all held together by rotation. The same principle drives far more violent systems. When two stars orbit each other too closely, their spins begin to tangle, gas is pulled from one to the other, forming a glowing accretion disk, a whirlpool of matter spinning at incredible speeds. Friction within that disk heats it until it blazes with X-rays. That's what we see around black holes, regions where spin pushes physics to its limit. A black hole that rotates doesn't just pull matter inward, it twists space itself. This phenomenon called frame dragging means that near a spinning black hole, space-time is literally being dragged around with it. Nothing can stay still, not even light. Photons are forced to swirl, bending around an invisible axis of infinite gravity. It's motion-devouring motion, chaos written into the fabric of reality. Even galaxies aren't immune. Their spiral arms look calm from a distance, but they're sites of constant tension, waves of gravity, gas collisions, and star formation, all competing at once. Some galaxies spin so fast that their outer stars should fly off into space, yet they don't. That's one of the mysteries that led scientists to propose dark matter, an unseen mass providing the extra gravity needed to hold them together. Without it, the universe's spin would tear itself apart. Spin creates beauty, but it also tests the limits of stability. Too little rotation and gravity wins, everything collapses inward. Too much, and the system shatters, flinging its material into space. The perfect balance lies somewhere in between, a razor's edge that nature somehow finds again and again. Even our solar system bears scars of that chaos. Craters on the Moon and Mars are the fossilized evidence of an age when orbits were unstable, planets shifted and collisions were frequent. Yet out of that turbulence came the stable clockwork we see today, a reminder that cosmic order often rises from chaos. Not despite it. Spin isn't a guarantee of harmony, it's a test of balance. Every rotating world, every orbiting star, walks the fine line between control and collapse, and that tension, that fragile equilibrium, is what makes the universe so alive. Most of the time, spin feels familiar. A planet turning a star, rotating a galaxy, swirling through space. But when you push spin to the extreme, it stops behaving like anything we know. It becomes something else, something that stretches the very rules of physics. Let's start with a neutron star. It's what's left when a massive star dies. The core collapses, crushing itself into a sphere, only about 20 kilometers wide, yet heavier than our sun. That collapse squeezes its rotation tighter, forcing it to spin faster and faster. Some neutron stars rotate hundreds of times per second. Their magnetic fields so strong, they shoot beams of radiation from their poles. Each pulse we detect on Earth marks a single rotation, a cosmic lighthouse flashing with perfect rhythm. We call them pulsars, and they are the most accurate natural clocks ever found. Even the best atomic clocks on Earth drift more than these stars do, but neutron stars are only the beginning. Spin them fast enough, and gravity wins the final battle. They collapse into black holes, and that's where rotation becomes truly alien. A black hole can spin at nearly the speed of light. At that point, the laws of physics warp. Space-time itself begins to twist, dragged around by the black hole's rotation. In a phenomenon called frame dragging, it's not a metaphor. If you orbited a spinning black hole, space itself would be moving around you, carrying you with it even if you tried to stay still. Inside this region, the ergosphere, motion is no longer optional. Everything must rotate, even light. Scientists call this type a Kerr black hole, and it's one of the strangest objects in the universe. Its spin defines its very structure. If it stopped spinning theoretically, the ergosphere would vanish, and the black hole itself would change shape. but there's no sign that ever happens. In fact, every black hole we've detected so far spins. The fastest ones, they complete a rotation in less than a millisecond. At those speeds, the energy locked in their spin can rival the output of entire galaxies. Some astrophysicists believe that jets of plasma shooting out from black holes, streams stretching thousands of light years, are powered not by falling matter, but by the black hole's rotation itself, through a process known as the Blandford-Znajek mechanism. Its motion transformed into pure energy, and beyond even that, there's quantum spin, the kind that lives inside the tiniest particles. Electrons, protons, and neutrons all have spin, but not the kind you can picture as a sphere turning. Quantum spin is intrinsic. It's built into their identity. It gives rise to magnetism, chemistry, and even the structure of matter. It's why atoms form the way they do, why the world is solid instead of collapsing into a blur of particles. Without spin at the quantum level, matter as we know it couldn't exist. So from the tiniest particle to the most massive black hole, spin defines everything. It shapes the visible and the invisible. It holds the universe together. And at its extremes, it shows us where our understanding ends. Because when motion approaches the speed of light, and spin begins to drag time itself, we realize something humbling, that the universe doesn't just spin in space-time, it spins space-time itself. It's easy to say that everything spins, but how do we actually know? How can we be sure that planets rotate, that stars turn, that galaxies swirl through space, when we can't even see most of them up close? The truth is, we've been watching motion for centuries, and nature has been showing us clues all along. The first real proof came from right here on Earth. In 1851, a French physicist named Léon Foucault suspended a giant pendulum from the dome of the Pantheon in Paris. He set it swinging back and forth and left it alone. To everyone's surprise, the direction of its swing began to slowly shift. The pendulum wasn't changing, the Earth was as our planet rotated beneath it. The swing appeared to twist, completing a full rotation every 24 hours. For the first time, humans could see our world spin, not as an idea, but as motion itself. A few decades later, telescopes revealed that other worlds moved too. By tracking the shadows of Jupiter's moons, astronomers noticed how the planet turned. They watched sunspots drift across the solar surface and measured the Doppler shift of starlight, the change in colour as one side of a star moves toward us and the other side moves away. From that subtle difference in light, we can tell exactly how fast a star spins, even from billions of kilometres away. In the 20th century, our tools became far sharper. Radio telescopes picked up the perfect rhythmic signals of pulses, proving that neutron stars rotate hundreds of times per second. Each pulse that reaches Earth is a heartbeat of cosmic spin. It's so precise that even the slightest irregularity tells us when a pulsar has collided, shifted, or slowed down, like listening to the gears of the universe itself. Then came space telescopes, Hubble, Chandra, Gaia, and now the James Webb. They don't just take pictures, they measure motion. Gaia, for example, tracks over 1 billion stars, recording their movements across the Milky Way, with an accuracy so fine that it can detect the subtle wobble of our Sun as planets tug on it while orbiting. From those wobbles, we've discovered thousands of exoplanets, new worlds each with its own spin and dance around its star. Even the rotation of black holes, once purely theoretical, has been measured by analysing X-rays emitted from the superheated disks of gas around them. Scientists can determine how fast the black hole must be spinning. Some rotate so quickly that the edge of space itself is dragged around at nearly the speed of light. The Event Horizon Telescope, which captured the first image of a black hole's shadow, showed that its ring glows brighter on one side, a direct result of rotation bending light itself. It's not an artist's impression, it's physics caught in the act. And the evidence doesn't stop there. Gravitational wave detectors like LIGO and Virgo, can now hear the spin of black holes and neutron stars as they merge. Each chirp in the data tells us how fast they were rotating. Before the moment they collided, we're not just observing light anymore. We're feeling the ripples of motion through space-time itself, from a swinging pendulum to signals across billions of light years. The message has never changed. Everywhere we look, every tool we build, every wavelength we observe, the universe keeps telling us the same thing. It's moving, constantly, endlessly, and through that motion, we've learned not only where we are, but that we are part of something still in motion, a living turning cosmos that never truly rests. When we talk about spin, we usually imagine rotation, something turning in space. But the truth is deeper. Spin is the hidden thread that ties the universe together. It links gravity, magnetism, light, and even the structure of time itself. Let's start small with electrons. Every atom in your body contains them, tiny particles carrying both charge and spin. That combination creates magnetic fields. In fact, every magnet, from the one on your fridge to Earth's own magnetic shield, exists because of the alignment of countless spinning electrons. Without that microscopic motion, magnetism wouldn't exist. Your compass wouldn't work. Solar winds would strip our atmosphere away. Spin is what stands between us and cosmic radiation. But spin doesn't just protect us, it organizes the universe. The way electrons spin determines how they arrange themselves in atoms, how chemical bonds form, and ultimately how matter behaves. If the rules of spin were slightly different, chemistry as we know it would collapse. Stars couldn't fuse elements. Life itself wouldn't have structure. Now scale that up. Spin also drives electric currents and planetary magnetism. Deep beneath our feet, molten iron moves and swirls as Earth rotates, creating the geodynamo, a self-sustaining magnetic field that shields the entire planet. Jupiter's rapid rotation generates a magnetic field, so enormous it stretches millions of kilometers into space, forming invisible wings of plasma that trap radiation and sculpt the planet's glowing auroras. Spin turns motion into magnetism, and magnetism in turn shapes the motion of matter. It's an endless feedback loop, a cosmic handshake between energy and movement. Even light itself, the fastest thing in existence, owes part of its nature to spin. A photon doesn't spin like a ball, but it carries intrinsic angular momentum, which gives it polarization, the direction in which its electric and magnetic fields vibrate. That's why polarized sunglasses can block glare, and why astronomers can decode the structure of distant galaxies. By studying the polarization of light reaching Earth, spin leaves its fingerprint in every beam of light that's ever crossed the cosmos. And then there's gravity, the grand architect of motion. Einstein's general relativity tells us that mass curves space-time, but when mass spins, it does more than curve, it twists. This effect, called frame dragging, means that rotation can literally drag time along with it. Near a massive spinning object like Earth or a black hole, time itself flows differently. The faster the spin, the stronger the twist. NASA's Gravity Probe B experiment confirmed this, measuring how Earth's rotation drags space-time by a few thousandths of a degree, a subtle, elegant proof that even our planet is slightly warping time as it turns. So from electrons to black holes, from the structure of atoms to the curvature of space-time, spin is everywhere. It doesn't just cause motion, it defines relationships. It links energy to matter, matter to magnetism, and motion to time. It's not an isolated phenomenon, it's a universal language. Every rotation, every orbit, every pulse in the universe is part of the same connected system, a cosmic choreography that ties all of existence together. Spin isn't just how the universe moves, it's how the universe communicates. Imagine the universe without motion. No planets orbiting, no stars turning. No atoms vibrating, only stillness. In that frozen reality, there would be no events, no change, and therefore no time. time at its most fundamental level isn't something the universe has. It's something the universe does. It's the measure of change, the rhythm of motion unfolding from one moment to the next, and spin more than anything else keeps that rhythm alive. Every rotation in the cosmos, a planet turning a pulsar, flashing an electron spinning, is a way of marking time. A single spin equals a single tick in the universe's clockwork. The faster the spin, the faster that clock runs. Without these cycles, there would be no reference for before or after. Spin gives structure to time itself. On the human scale, this feels familiar. We measure days by Earth's rotation, years by its orbit around the Sun. Even the oscillations of atoms, their internal spins flipping back and forth, form the basis of atomic clocks, which are so precise they lose only a second every 100 million years. Every tick of time we know comes from motion, from something turning, vibrating, or repeating, but the connection goes deeper than calendars and clocks. In physics, time and energy are intertwined, and motion, especially rotational motion, is one of the purest forms of energy there is. When something spins, it has kinetic energy, and as it loses that energy through friction, radiation, or collision, it moves toward equilibrium. That gradual loss of order called entropy is what gives time its direction, forward. If all motion were to stop, entropy would stop increasing, and time as we understand it would freeze. That's not poetry, it's thermodynamics. The arrow of time we experience exists because energy is always moving from organized to disordered states. Spin is one of the key ways that process unfolds. It's how stars distribute energy, how galaxies evolve, how the universe itself avoids collapse into static perfection. And then there's relativity. Einstein's revelation that time is not absolute. The faster something moves, the slower time flows for it compared to an outside observer. That means spin literally changes how time passes. A rapidly spinning neutron star, for instance, experiences time differently from the space around it. A spinning black hole twists both space and time into a single inseparable fabric. In these regions, motion doesn't just mark time, it creates the conditions for time to exist at all. Every spin in the universe, from the smallest electron to the largest galaxy, is a tiny clock, each beating at its own rhythm. Together they make the great symphony of time we all move through. So when you look up at the stars, you're not just seeing distance, you're seeing history in motion. Every turn, every orbit, every flicker of light is a story of time being written in rotation. Without motion there would be no change. Without change, no time. And without time, the universe would be silent. Spin isn't just how things move through time, it's how time moves through everything. Every world begins with a turn. Billions of years ago, long before Earth existed, our solar system was nothing but a swirling cloud of gas and dust. It wasn't a calm place, it was turbulent, full of collisions, and everywhere gravity was pulling matter together. But even in that chaos there was a pattern, a faint collective spin, and that spin changed everything. As gravity drew material inward, the cloud began to flatten, forming a massive rotating disk around the newborn sun. This wasn't coincidence, it was the natural outcome of angular momentum. When you take something vast and collapsing, it has to spin faster to conserve motion. That rotation prevented the disk from collapsing completely. It held the system together long enough for dust to stick clump and grow into planets. Each world that formed inherited its share of that original spin. That's why nearly all planets orbit the sun in the same direction, and along roughly the same plane, a flattened remnant of the disk that birthed them. Even today, billions of years later, the ancient rotation still defines the shape of our solar system. We are literally living in the fossil imprint of a motion older than Earth itself. Spin didn't just shape the orbits of planets, it built their character. When a planet spins on its axis, it creates day and night, sets the rhythm for weather, wind, and temperature. Without spin, Earth's days would last forever. its one side burning while the other froze in darkness. But rotation mixes light and shadow, distributing energy and making our world habitable. Even the tilt of that spin matters. Earth's 23.5-degree axial tilt creates the seasons, gentle cycles that allow life to adapt and thrive. If that tilt was smaller, our climate would stagnate. If it were larger, seasons would swing violently from extreme heat to ice. Our world's balance, its life-friendly rhythm, exists only because its spin is just right. And we're not unique. Every planet's rotation writes its own story. Mercury spins so slowly that one day lasts nearly 2 Earth months. Venus spins backward, its thick clouds locked in a perpetual slow-motion swirl. Mars spins almost like Earth, giving it familiar days, but its smaller size makes its climate more fragile. Then there's Jupiter, the giant that spins so fast it completes a day in just 10 hours. That furious rotation drives storms larger than entire planets, like the Great Red Spot, a vortex that has raged for centuries. Even moons bear the mark of spin. Our moon rotates exactly once per orbit around Earth, which is why we always see the same face. It's locked in a perfect balance, a cosmic handshake between gravity and rotation, known as tidal locking. Without that equilibrium, the moon's gravitational pull would constantly shift, tearing Earth's oceans apart. And spin doesn't stop at planets. Asteroids tumble chaotically, comets twirl as sunlight heats their icy surfaces, and even dust grains in interstellar clouds rotate as they absorb light. At every scale, spin organizes matter, turning chaos into structure, randomness into rhythm. Our world was not built in silence. It was sculpted by motion, the slow, patient rotation of dust and stone under the pull of gravity. Spin gave it shape, gave it weather, gave it seasons, and ultimately gave it life. Every sunrise, every ocean current, every heartbeat is part of that ancient rotation still unfolding. We live on a spinning world, born from a spinning star, in a universe that has never stopped turning. If the universe loves order, why doesn't everything spin the same way? At first glance, it almost seems like it does. Most planets orbit the Sun in the same direction. Most galaxies spiral clockwise or counterclockwise depending on how we see them. But look closer and you'll find small imperfections, tiny cracks in the universe's symmetry, and those cracks might hold the key to how everything began. Take our solar system. Nearly all planets orbit in the same direction, a memory of the primordial disk that created them. Yet 2 worlds defy the rule. Venus spins backwards, and Uranus rolls on its side, its poles pointing nearly at the Sun. These are not accidents. They are scars, evidence of massive ancient impacts that changed their spin forever. The universe doesn't erase history, it keeps it in motion. But a symmetry runs deeper than collisions. When astronomers studied thousands of galaxies, they noticed something strange. A tiny excess of galaxies spinning in one direction over the other. It's not much, maybe 1 or 2%, but it's enough to make scientists wonder whether the entire universe itself has a subtle global rotation. If that's true, it could mean that the cosmos has a preferred direction, a faint echo of the conditions from the Big Bang. Even at the smallest scales, nature isn't perfectly balanced. In the quantum world, particles and their mirror opposites don't behave exactly the same. This phenomenon, called parity violation, was first discovered in the 1950s. Physicists expected the laws of nature to look identical if you flipped them like a mirror, but when they tested it with decaying atomic nuclei, the results shocked everyone. Particles preferred one spin direction over the other. The universe, it seemed, had a handedness. That discovery changed physics forever. It proved that symmetry, one of nature's most beautiful principles, can be broken, and that breaking may be the reason we exist at all. If matter and antimatter were created in perfect balance, they would have annihilated each other instantly after the Big Bang. but something perhaps a tiny difference in spin, a microscopic bias in how particles decayed, gave matter the slightest advantage. That tiny imbalance was enough to leave behind the atoms that formed stars' galaxies, and eventually us. Spin may be the fingerprint of that ancient choice, a subtle preference written into the laws of physics that tip the scales toward existence. It's not just a mechanical motion, it's a clue to why there's something rather than nothing. So when you look at the spiral of a galaxy, remember that swirl might not be random. It could be the universe's own signature, a direction written into its very birth certificate in a cosmos that values balance. It's the tiny imperfections, the small breaks in symmetry that make everything possible. If the universe had been perfect, it might never have existed. Perfection means balance, a stillness where every force cancels another. And in that silence, nothing could move, nothing could grow. The universe needed a flaw, a tiny deviation to begin. In the first moments after the Big Bang, there was no symmetry, no calm, just energy, dense, chaotic, trembling with possibility. But within that chaos, some regions had slightly more matter, some with slightly more spin, some with just a bit less. Those minuscule differences, 1 part in 100,000, were enough to break the perfect mirror of the newborn cosmos. From that broken symmetry, everything we know began to unfold. Matter triumphed over antimatter. Gravity gathered the uneven fog of plasma into knots. Each knot spun a little differently, some clockwise, some counterclockwise, and those subtle twists became the seeds of galaxies. So imperfection, not perfection, is what shaped creation. It's what allowed energy to flow and time to move forward. If symmetry had never broken, the universe would have remained a flat, uniform sea of radiation. No stars, no planets, no life. Stillness would have been eternal death. But because of that imbalance, that one small cosmic bias, the universe began to turn. Every star, every world, every atom we know is a ripple born from that first tiniest symmetry. It's the universe's way of remembering that perfection isn't fertile, motion is. And motion was born not from order, but from the courage of chaos to be slightly uneven. Maybe that's the deepest truth written in the cosmos. That beauty is not symmetry, but the dance between opposites. Every spiral, every orbit, every rotation is the echo of that original imperfection that gave the universe permission to move. The universe didn't begin with peace. It began with imbalance. And in that imbalance it found direction. Imagine rewinding time back beyond galaxies, stars, or atoms, to the instant when the universe was smaller than a grain of sand, a trillion times denser than the core of a star, and unimaginably hot energy condensed into pure potential. In that chaos, quantum fields rippled wildly. Tiny fluctuations appeared wrinkles in the fabric of reality itself, each one a surge of energy, a miniature whirlpool of motion. These weren't just random waves, they carried spin, microscopic twists in space-time. The universe's first rotational fingerprints. Then came inflation. In less than a heartbeat, the universe expanded faster than light, stretching those subatomic eddies into cosmic vortices. Tiny quantum spins became vast swirls of matter and energy, their imprints frozen into the geometry of the cosmos. The first galaxies billions of years later would trace their shapes along those invisible currents. That was the first spin. The moment motion became destiny. It wasn't a rotation in space, it was the rotation of space. The laws of physics, gravity, electromagnetism, quantum mechanics were still crystallizing, but one principle was already in place. Motion cannot vanish, only transform. As the universe cooled, quarks spun together into protons and neutrons. Those combined into atoms, their electrons spinning in probability clouds, echoes of the first motion. Every atom in your body still carries that memory, a relic of the universe's original spin. If you could have stood there, in that first instant when time began to tick, you wouldn't have seen light or heard sound. you would have felt motion itself, twisting reality into existence. From that first turn, everything followed. The swirl of galaxies, the orbit of planets, the heartbeat of life. The first spin was the moment when chaos learned to dance, and the universe took its first step toward becoming self-aware. Time did not arrive as a finished highway. It emerged as a path beaten by motion. In the newborn universe, change was the only certainty. Fields fluctuated, particles flickered into being, and space itself stretched. But change needs a measure, a reliable tick, or it dissolves into noise. Spin provided that tick. A rotation is a promise. Begin here, return here. One turn defines a unit. From the first vortices stretched by inflation motion began to loop, and every loop gave time a foothold. Electrons carried intrinsic spin, a built-in rhythm that never winds down. Atomic nuclei precessed like tiny tops. As matter cooled and combined, these microscopic metronomes multiplied, writing a lattice of cycles into the fabric of reality. Yet time's arrow did not point forward merely because clocks began to tick. Direction required a preference. The universe chose its bias through a chain of subtle decisions. As the hot plasma thinned out of equilibrium, reactions froze in the memory of matter. Charge parity violation. The delicate asymmetry and particle decays tipped the balance just enough for matter to endure. With each frozen choice, entropy increased. Energy spread from concentrated to diffuse, and the arrow of time lengthened. Spin made that spread orderly rather than catastrophic. Consider a collapsing cloud of gas. Gravity pulls inward. Rotation resists collapse, and the cloud flattens into a disk. Angular momentum does not vanish, it redistributes. What could have been a chaotic crash becomes a controlled spiral. The same logic played out across the early universe. Eddies diverted energy into orbits, orbits into rotations, rotations into enduring structures. Motion slowed the rushed equilibrium, buying time for complexity to appear. Quantum mechanics added one more ingredient: selection. In the furnace of the first second, states interfered like overlapping waves. But as the cosmos expanded, interactions with the environment forced choices. Quantum possibilities decohered into outcomes, and many of those outcomes carried rotational character. Where a phase could wind it wound, where a field could twist it twisted. Spin became the signature of decisions made and kept. Now imagine the first clocks coalescing out of that tumult. A pulsar is the end state of a massive star, but its idea was present from the start. A compact object whose rotation is so steady that its period can define time. Long before pulsars existed, the embryo of that possibility was alive in the rules governing spin and conservation. The universe prepared the tools of precision while it was still learning to cool. Time also learned to bend. Rotation does not only mark time, it shapes it. Where mass spins, space-time twists. Even in those early epochs, frame dragging was written into the equations, a quiet guarantee that motion and time would never be separable. Later, around fast-spinning black holes that twist would become vivid. Clocks near the whirl would disagree with clocks far away, but the principle was ancient. To rotate is to edit the tempo of time. On human scales, we borrow this inheritance. We count days by Earth's spin, seasons by its tilt, years by its orbit. Our most precise instruments measure the flips of atomic spin. All of our language for before and after rests on cycles that began when the universe first found the courage to turn. If time is the story of change, spin is the punctuation that makes the story readable. A world without rotation would still possess events, but they would smear into one another like ink without lines. With spin, events recur. Recurrence breeds expectation. Expectation invites memory. And memory is the foundation of meaning. When did time begin to turn? The honest answer is, when motion learned to return. From the first closed paths in quantum phases to the grand orbits of galaxies, the universe taught itself to keep time by moving in circles. The arrow points forward because entropy demands it. But the ticks that let us hear that arrow are born of rotation. Which brings us to a deeper question. If time can be heard, what does it sound like when the cosmos first starts keeping the beat? Before there were stars, the universe could sing. Not with air, not with strings, but with gravity and light. In the first 380,000 years, the cosmos was a hot plasma, where photons and baryons were locked together. Push that fluid in one place and it rebounded in another. Compression followed rarefaction in a steady rhythm. These were not metaphors. They were real pressure waves. Acoustic oscillations written across space. Every wave had a tempo set by the speed at which light and matter could communicate. The larger the region, the deeper the note, the smaller the region, the higher the pitch. Rotation joined the choir by adding vorticity. Tiny curls that tried to twist the fluid as it rang. Most curls decayed, but not all. Where the cosmic medium could carry a hint of swirl, it did, and that swirl modulated the melody. Inflation. The great stretcher of scales had prepared the score. It amplified quantum fluctuations and laid down phases with uncanny coherence. When the plasma began to sing, those phases ensured that distant regions were in step, like drummers hearing the same downbeat across a desert. The universe did not hum randomly. It performed a piece with recognizable motifs. We can still read the sheet music. When atoms finally formed and the fog cleared, the last light of that era set off on a journey across 13.8 billion years. We call it the cosmic microwave background. Frozen in its faint glow are the fingerprints of those ancient notes. Hot spots and cold spots, peaks and troughs that match the overtones of a resonant cavity the size of the young universe. There is a deeper channel beneath that light, gravity itself. Long before the plasma decoupled space was shaking, primordial, gravitational waves, ripples in the geometry raced outward at light speed. They carried no charge left, no trail of ions, and could pass through matter as if it were fog. Where they met the photon sea, they imprinted a subtle twist in the polarization of the light, a curl-like pattern that researchers are still chasing across the sky. Detecting those curls cleanly would be like hearing the opening bar of creation with our own ears. Spin does not merely accompany these waves, it powers their structure. A rotating mass distribution radiates gravity the way a struck bell radiates sound. In the early universe, patches that carried angular momentum tried to whirl even as the fluid resisted. That struggle wrote side bands into the spectrum-gentle distortions that later growth would translate into the preferred alignments of galaxies and the winding of the cosmic web. Listen closely to what the data say. The spacing of the acoustic peaks tells us the tempo of expansion. The relative heights tell us how much ordinary matter, dark matter and radiation were present in the orchestra. The polarization patterns whisper about twists, rotations, and the faint hand of gravity waves. From a handful of harmonics, we can reconstruct the hall, the instruments, and the players. If you could stand in that young universe, you would not hear the way we hear. Your eardrums would find no air to shake, but your instruments would register a polyphony of oscillations, density waves, sloshing curvature waves, rippling and rotational modes trying to catch hold. You would witness a chorus in which motion is both melody and meter. The song did not end when the plasma cleared. As gravity took over, waves broke into structures. Crests became clusters, troughs became voids, and the beat lengthened as expansion slowed the dance. Galaxies found the downbeats at the nodes of filaments. Where flows converged with a twist, disks formed and starbirth ignited. Spin turned the score into architecture. There is poetry in this, but there is also restraint. The universe is not a free improvisation. It is a theme and variations played with crystalline discipline. Conservation laws keep rhythm. Initial conditions set key and tempo. Non-linear growth writes the solo passages. And across the entire performance rotation adds grace notes that make the piece unforgettable. When we build detectors to catch gravity's faint tremors, we are not only chasing technical glory, We are tuning our ears to the first music ever performed. Each chirp from merging black holes is a late movement and encore in a hall full of ancient echoes. To reach the overture, we must follow the harmonics back through the microwave background into an age when sound and spin were the same language. The overture is almost done. In the next act, the melody condenses into visible form. Ripples become rivers. Rivers braid into a web. The web winds itself into spirals. From the sound of creation, we step into its sculpture, and there at the crossroads of waves and whirlpools, the first galaxies learn to turn. By the time the universe was a few 100,000 years old, its song had faded into silence. The light that once scattered in every direction now streamed freely the cosmic microwave background, but the echoes of those early oscillations remained imprinted in matter itself. Tiny over densities, just a few parts in 100,000, became the scaffolding of everything to come. Gravity took the stage. Where the density was slightly higher, matter began to fall inward. The collapse wasn't smooth, it carried memory of motion. Every knot of gas and dark matter inherited a faint spin from the surrounding currents. Vorticity seeded during inflation amplified by turbulence. The universe had stopped singing, but it had begun to dance. As regions collapsed, conservation of angular momentum worked relentlessly. The same principle that makes an ice skater spin faster as she pulls in her arms applied on a cosmic scale. As halos of gas shrank, their rotation quickened. The first proto-galaxies were born not as still clouds, but as spinning storms of gas and dark matter. Computer simulations today like Illustris and Eagle recreate this process in exquisite detail. They show filaments of dark matter winding across the universe, intersecting at nodes where galaxies ignite. Each filament carries angular momentum along its length, feeding newborn galaxies with rotational energy like rivers feeding whirlpools. The pattern is astonishingly consistent. Galaxies don't just appear randomly distributed. They align with a cosmic web that birthed them. Their spins often trace the flow of dark matter, a silent reminder that even the invisible parts of the universe know how to turn. The physics behind it is simple yet profound. In an expanding universe, collapsing regions must shed excess angular momentum to settle. They do this through tidal torques, gravitational tugs between neighbouring structures that twist each other as they form. It's a cosmic exchange of spin. One region slows while another speeds up, ensuring the total angular momentum of the universe remains conserved. Over billions of years, this dance of torque sculpted the familiar shapes we see today. Disks, spirals, bulges, bars, each a frozen expression of angular momentum seeking equilibrium. The Milky Way itself is one of these survivors, its stars orbiting the galactic center like pearls on a spinning string. Each motion a continuation of that first ripple in the early plasma, from the subatomic twist to the galactic swirl. The same principle repeats. Motion once begun persists. The ripples of creation became rivers of rotation, and those rivers over time carved the architecture of the cosmos. Every galaxy tells a story written in its spin. Some are grand spirals, their arms stretched like cosmic whirlpools. Others are smoother lips, still turning but quietly. Their early energy dispersed by collisions and mergers. Each morphology is a fossil record of motion. Why do galaxies take different forms? The answer lies in the balance between angular momentum and gravity. A galaxy born with high spin retains its disk shape, its rotation counteracting collapse. Low-spin systems, on the other hand, let gravity pull their material inward, forming rounder, more spheroidal shapes. In this way, spin isn't just a property, it's destiny. Observations from the James Webb Space Telescope are beginning to glimpse this architecture at its origin. Galaxies only a few 100 million years old already show rotation, some spinning at over 200 kilometers per second. That's astonishing because in such a young universe, there has barely been time for multiple rotations to occur. It means that spin isn't something galaxies acquire later. It's built in from the start, a direct inheritance from the primordial currents of the cosmos. But rotation doesn't just define shape, it governs how galaxies live and die. Fast-spinning disks channel gas along stable orbits, sustaining star formation for billions of years. When galaxies collide, their spins can either merge harmoniously or clash destructively. Aligned spins form vast rotating giants. Opposite spins cancel, creating turbulent spheroids that stop birthing stars. Angular momentum decides whether a galaxy thrives or fades. Dark matter again plays the invisible conductor. Simulations show that halos of dark matter spin, guiding the orientation and stability of the luminous matter within. The stars we see trace patterns drawn by forces we cannot see, following the hidden scaffolding of dark energy and dark matter. Even the elegant spirals of galaxies like Andromeda or the Milky Way are surface ripples on deeper invisible vortices. The most beautiful revelation is that this pattern scales indefinitely. The same equations describe a hurricane, a galaxy, and a supercluster. Rotation provides stability amid chaos, a universal principle that governs every whirl of matter, from storm clouds on Earth to the largest structures in the observable cosmos. So when you look at a spiral galaxy, its arms gracefully winding around a luminous core, you're seeing the geometry of motion made visible. Each curve is a trace of physics as old as the Big Bang, each orbit a note in the great harmony of spin, and though we measure it with telescopes and equations, its essence remains simple. The universe is not built on stillness, but on the quiet, eternal turning that holds it all together. Every spin in the universe is temporary, not because it fades, but because it gets shared. Galaxies, for all their grace, are not isolated dancers. They move through a crowded ballroom, drawn together by invisible threads of gravity, and when two galaxies meet, their spins begin to speak. Collisions between galaxies look catastrophic, yet they unfold in slow motion, millions of years of gravitational choreography. From a distance, it seems as though they simply pass through one another, their stars rarely colliding head-on, but their motions, their angular momenta intertwine. Tidal forces stretch each galaxy like taffy, pulling out long arms of stars and gas that curve into glowing bridges. The result is not destruction, but transformation. In those colossal interactions, spin is rewritten. A galaxy's angular momentum can double split or even reverse, depending on how it meets its partner. If two disks rotate in the same direction, their spins merge, the remnant becomes a massive fast-spinning spiral or lenticular system. But if they collide in opposite directions, the violent tug-of-war tears their ordered motion apart, leaving behind a rounder, slower, rotating elliptical galaxy. Astronomers call this process violent relaxation, an ironic phrase for something that ends in stillness. Even so, nothing truly stops. The debris of these encounters doesn't vanish. It redistributes motion. Streams of gas collapse into new rotating disks. Some form rings, others form polar structures that orbit perpendicular to the old plane. In every case, angular momentum is conserved, never destroyed, only reimagined. Our own galaxy bears the scars of such encounters. The Milky Way is not a solitary creation. It was built from dozens of smaller galaxies consumed over billions of years. Astronomers can still trace the fossil trails of those mergers, streams of stars orbiting at odd angles, remnants of ancient collisions. Even now, the Milky Way is drawing the Sagittarius dwarf galaxy into its halo, absorbing its stars and stretching it into a ribbon of light that loops around the sky. And a far greater meeting lies ahead. In about 4 billion years, the Milky Way and Andromeda will collide. Simulations predict that their central black holes will spiral together, dragging the surrounding stars into vast tidal arcs. Over billions of years, they will settle into a single enormous elliptical galaxy, an object astronomers have already nicknamed Milkomeda. The spiral arms that define our night sky will dissolve, but the total spin, the combined angular momentum of both systems, will remain redistributed across a new form. What may look like an ending is in truth a recycling of motion. Each collision mixes angular momentum like colours of paint, chaotic at first but ultimately creating new shades of structure. This cycle of merger and rebirth is one reason the universe never stagnates. Spin ensures continuity. Every generation of galaxies inherits the momentum of its ancestors. These grand interactions even shape how galaxies evolve internally as they collide gas funnels toward their centres, feeding bursts of star formation and awakening dormant black holes. Those black holes spin faster as they consume matter, and their jets, powered by rotational energy, can stretch across hundreds of thousands of light years, regulating the growth of their host galaxies. Spin drives creation, then restrains it, a feedback loop as elegant as it is violent. It's humbling to realize that even chaos follows law. Every distorted spiral, every glowing bridge between galaxies is the visible signature of angular momentum doing its work, balancing gravity's hunger with motion's persistence. Collisions may reshape galaxies, but they also remind us that rotation is not fragile. It adapts, transfers, endures. When galaxies collide, they're not fighting, they're conversing, exchanging their stories of motion. And through that cosmic conversation, the universe writes its next chapter of rotation. Every galaxy spins, yet the visible matter alone cannot explain why it holds together. If we add up all the stars, gas and dust, their combined gravity is far too weak. At the speeds we observe, galaxies should fly apart, their outer stars flung into the void like sparks from a wheel. But they don't. Something unseen holds them in its grasp. Something massive, silent, and everywhere. We call it dark matter. It does not emit light, reflect it, or absorb it. It does not collide, clump, or glow. And yet it outweighs everything we can see by a factor of 5. It forms vast halos around every galaxy, invisible cocoons of mass that extend far beyond the starlight. Without those halos, rotation would make galaxies unstable. Spin would tear them apart. Dark matter provides the anchor, the unseen counterweight that lets spin endure. The evidence is unmistakable. When astronomers measure the orbital speeds of stars within galaxies, they find a mystery. The farther from the centre, the faster stars move, a direct violation of Newton's expectations. Instead of slowing down, the rotation curve remains flat, as if an unseen hand keeps the outer stars in orbit. That hand is the gravitational influence of dark matter. It holds the spinning disk together the way air pressure holds a tornado's column intact. On even larger scales, dark matter is the architect of cosmic spin. In the early universe, its particles move slowly. Unhindered by radiation pressure, they began to collapse into filaments long before ordinary matter could cool. As those filaments grew, they twisted, channeling angular momentum through gravitational torques. Normal matter baryons simply fell into these spinning scaffolds, taking on the rotational energy of the dark structures beneath. Every galactic spin, from the smallest dwarf to the grandest spiral, is a visible echo of a dark rotation that began billions of years earlier. Computer simulations reveal this hidden choreography. When scientists model the universe with and without dark matter, only the dark matter version gives rise to realistic galaxies. Without it, disks fail to form, and the few that do cannot maintain coherent spins. Dark matter doesn't just shape galaxies, it teaches them how to turn. Even more intriguingly, the orientation of galaxies spins across the sky still carries memory of those primordial dark flows. Large surveys like the Sloan Digital Sky Survey and the Euclid mission find subtle correlations between the direction of galactic rotation and the structure of the cosmic web itself. The pattern suggests that dark matter is not merely a static background, but a dynamic participant, a kind of gravitational field that spins back. Some theories even propose that dark matter's nature is tied to spin at the quantum level. If it is made of ultralight particles, axions perhaps, their collective behaviour could form macroscopic vortices, rotating condensates on cosmic scales. Others imagine dark matter as particles with intrinsic spin that interact only through gravity, subtly influencing how galaxies align and evolve. Whatever its form, its fingerprints are everywhere rotation endures. Without dark matter, there would be no graceful spirals, no stable orbits, no long-lived motion. Gravity alone cannot balance the energy of spin. It needs the invisible framework that dark matter provides. The universe's great ballet depends on unseen dancers moving beneath the stage. It's a reminder that most of what governs the cosmos lies beyond the light we can see. We live in a universe whose motion is written in shadows, a symphony performed by matter we do not yet understand, but whose rhythm keeps every galaxy turning. And if dark matter is the stage upon which the visible universe spins, then perhaps what lies beyond it, dark energy, is the rhythm that drives the entire performance forward. If you could step outside the universe and watch it from afar, you would not see chaos. You would see rhythm. Across billions of light-years galaxies are not scattered randomly. They trace vast filaments of invisible matter, woven into a structure so intricate that astronomers call it the cosmic web. Each filament connects to others at luminous intersections, clusters of galaxies rotating around shared centers of gravity, and though each galaxy spins on its own axis, together they form a choreography so immense, it might as well be a symphony of motion. This web is the universe's grand composition. Gravity is its conductor, and angular momentum its music. The pattern of spin alignment across these filaments reveals that galaxies don't rotate in isolation. Their spins tend to line up with the direction of the filaments they inhabit, as if responding to a deeper cosmic current. It's as though the entire cosmos inherited a single rhythm. From its earliest fluctuations, a faint echo of the turbulence that followed inflation. Astronomers have begun to measure this alignment directly. Large surveys like the Sloan Digital Sky Survey, and more recently the Euclid and DESI missions, map the position, velocity and spin direction of millions of galaxies. What they've found is astonishing. Spiral galaxies near the edges of filaments often spin along the filament, while those near the dense nodes, the intersections, tend to spin perpendicular to it. The universe appears to be winding itself like a colossal screw, turning energy and matter into a coherent, rotating architecture. This phenomenon isn't just poetic, it's physical. The same tidal torque forces that gave individual galaxies their spin also acted on the vast filaments of dark matter. As matter flowed inward, it twisted those filaments, and the galaxies that later formed within them retained the direction of that twist, its angular momentum on the largest scale imaginable. The cosmic web itself turning ever so slowly, under the influence of gravity and time. Even the polarization of light from distant galaxies seems to reflect this hidden symmetry. Photons stretched by the expansion of space carry a subtle memory of the direction they came from, a polarization pattern shaped by ancient rotational flows. By studying these patterns, scientists can trace the earliest cosmic vortices that still echo through today's universe. If we could accelerate time watching the universe evolve in a few minutes, the sight would be mesmerizing. Filaments twisting clusters, merging galaxies, spinning like notes in a melody, each movement influencing the next. The expansion of space would act as the tempo, gravity the drumbeat, dark matter the bass line that holds it all together. The luminous galaxies, the visible notes, would shimmer, merge and resonate. A visible harmony born from invisible physics. This is why astronomers often speak of cosmic coherence. It's not mystical, it's mathematical. The laws of motion apply everywhere, and through billions of years of gravitational evolution, they've produced not randomness, but resonance, a pattern that repeats across scales, from the smallest particle spin to the turning of superclusters. And maybe that's the universe's most elegant truth. Order and motion are not enemies. They are partners. Each turn, each orbit, each vibration, feeding back into a greater design. So when we gaze through telescopes at galaxies billions of light years away, we're not just seeing light from the past. We're seeing the rhythm of the universe made visible, a silent symphony, still playing the song that began with the first spin. The universe has always turned, but at some point that cosmic motion found a new expression in chemistry and molecules in life. Long before planets cooled or oceans formed, rotation was already shaping the invisible architecture of matter. Atoms do not sit still. Their electrons spin not metaphorically but literally. Spin is a built-in quantum property, the tiny magnetic heartbeat of every particle, and it is this microscopic motion that makes chemistry possible. When electrons spin in opposite directions, they pair, forming stable bonds. When they align, they repel, creating magnetism. Every molecule in your body is defined by this dance of spins, an interplay of attraction and resistance, symmetry and asymmetry. But the story becomes even stranger when we look at chirality, the handedness of molecules. Some molecules exist in two mirror forms, one left-handed, one right-handed, chemically identical yet biologically incompatible. Your amino acids, the building blocks of life, are exclusively left-handed. Your DNA spirals to the right. This bias, this microscopic preference, is one of the great mysteries of biology. Why does life choose one spin over the other? In the laboratory, when we synthesize amino acids artificially, we get equal parts left and right, but nature does not. Every cell on Earth obeys a single direction, a universal asymmetry, as if chemistry itself remembers the universe's original imbalance. Some scientists think the answer lies in cosmic spin itself, polarized light from newborn stars, or the magnetic fields of supernovae might have destroyed one molecular orientation more readily than the other, leaving a surplus of left-handed precursors drifting through interstellar clouds. Meteorites that landed on early Earth, like the famous Murchison meteorite, contain amino acids with this same bias. The seeds of our biological asymmetry may have been sown in the spinning clouds of space. Others suggest that fundamental forces, like the weak nuclear interaction, already broke symmetry billions of years earlier. In particle physics, left-handed neutrinos dominate the universe, a tiny clue that nature itself prefers one spin orientation. Perhaps that subtle quantum preference echoed upward through chemistry, life simply following the direction physics had already chosen. Whatever the origin, the result is profound. Life is not balanced, it's biased. And that bias is what gives it direction. A mirror version of Earth, built from right-handed amino acids and left-handed sugars, would look identical from afar, yet its biology would be incompatible with ours. Even our enzymes, the molecular machines that build and repair life, depend on the right kind of twist. Reverse that twist, and the entire machinery of biology grinds to a halt. It's a reminder that rotation once again decides fate. From galaxies to genes, spin separates what can exist from what cannot. Our very existence depends on this cosmic preference, a faint whisper of asymmetry that began billions of years before life itself. The DNA double helix, that elegant ladder spiraling through every living cell, is not just a symbol of life. It is a monument to motion. Each twist, each turn, is the echo of the universe's earliest rotations, translated into the language of biology, and perhaps that is the hidden poetry of existence. Life didn't invent motion, it inherited it. Every world spins, but not every world is alive. The difference often lies in what that spin creates beneath the surface. Deep below our feet, far beneath the crust and mantle, lies a sea of molten iron and nickel, a planet's beating heart of metal. It churns and roils like a slow, fiery ocean, its currents driven by heat escaping from the core, and by the planet's own rotation. From that restless motion an invisible miracle is born. Earth's magnetic field. This field is not static, it is a living phenomenon of motion. As molten metal moves through the core, charged particles create electric currents. Those currents generate magnetic fields, and the planet's rotation aligns them into a coherent global shield. We call this process the geodynamo. It is one of the most complex yet most elegant machines in the universe. A self-sustaining generator powered by spin. Without it, Earth would be defenseless. Our atmosphere would be slowly stripped away by the relentless wind of charged particles streaming from the sun. Every flare, every coronal mass ejection would erode the air that protects us. The auroras that dance at the poles, beautiful curtains of light, are merely the visible edge of this defense. They are the battle scars of a planet that spins fast enough to survive. We don't have to imagine a world without this protection. Mars offers the perfect cautionary tale. Once it too had a molten core and a global magnetic field. But as the small planet cooled, its core solidified and its dynamo stopped turning. The shield vanished. Solar wind swept its atmosphere into space, leaving behind a cold, dry desert where rivers once flowed. Its surface today is bombarded by radiation, its sky thin and silent. Mars spins, yes, but it no longer spins deep. Jupiter, by contrast, is a giant engine of magnetism. Though made mostly of hydrogen, its immense pressure turns the gas metallic near the core. Combined with Jupiter's rapid 10-hour rotation, this metallic hydrogen generates the strongest magnetic field of any planet in the solar system, so vast it could hold 15 Earths inside. It funnels radiation into deadly belts, but it also creates auroras hundreds of times brighter than ours, a testament to how powerfully rotation can sculpt invisible forces. Even our moon bears the imprint of spin and magnetism. It once had a weak dynamo of its own, likely driven by tidal interactions with Earth, a magnetic echo that faded as the moon's core cooled. The frozen magnetic patterns on its surface are relics of that long-lost internal motion, tiny fossils of an ancient planetary heartbeat. For Earth, though, the heartbeat continues. Every day our planet's rotation keeps the liquid core turning, sustaining the shield that makes life possible. And that shield does more than block radiation. It stabilizes our atmosphere, guides animal migration, and even shapes the behavior of our technology. Every compass, every satellite, every GPS signal is quietly tracing the lines of a magnetic field born from planetary spin. It's humbling to realize that our survival depends not on something we can see, but on emotion we can only feel indirectly. The slow, unseen turning of molten iron, miles beneath our feet. Spin gave us chemistry, spin gave us magnetism, and together they gave us a home that endures. So when you watch the aurora shimmer across the polar sky, remember what you're really seeing, the proof that our planet is alive inside, that deep within its heart, the universe's oldest rhythm, the rhythm of rotation, still plays on. Not too fast, not too slow. Our world spins at a pace that seems ordinary, one rotation every 24 hours. But that rhythm is no accident. It is the quiet balance that makes life possible. If Earth spun much faster, days would be shorter. Winds would roar across continents at hundreds of kilometers per hour, and the atmosphere would stretch into violent, unstable bands. Centrifugal force would push oceans toward the equator, flooding lowlands and leaving the poles exposed and dry. Mountains would erode faster, storms would rage longer, and gravity at the equator would feel slightly weaker, just enough to shift the delicate balance of air, sea, and land. That sustains our climate, but if Earth spun more slowly, the opposite disaster would unfold. Days and nights would last for weeks. Under the long daylight, one hemisphere would bake beneath unending heat, while the other froze in darkness. The atmosphere would struggle to circulate, creating deserts of fire and continents of ice. The oceans might still move, but they would carry heat too slowly to rescue either side. life as we know it dependent on cycles of temperature, light and darkness would never have formed. Our 24-hour rotation is a compromise sculpted by time. When Earth was born, it spun much faster. A day lasted barely 6 hours, but over billions of years. Gravitational tides from the moon slowed that rotation. The same friction that makes ocean tides rise and fall acts as a brake, converting rotational energy into heat. Each century Earth's day lengthens by about 2 milliseconds. It's almost imperceptible, yet it means that long after we're gone, our descendants will live on a planet that turns a little slower, its clock forever changing by the gentlest touch of gravity. That slowing paradoxically stabilized everything. A faster Earth would have torn its atmosphere and crust more violently. A slower one would have lost its magnetic dynamo sooner. But this middle ground, this just right spin, gives us both climate and protection. It creates predictable rhythms. Day and night, wind and rain, wake and sleep. Spin set the tempo, and life evolved to dance to it. Our very biology is tuned to this rotation. Every living organism on Earth, from bacteria to blue whales, follows a circadian rhythm that mirrors the planet's daily spin. Inside every cell, molecular clocks tick in harmony. With the rising and setting of the sun, these cycles control when we eat, when we rest, when we heal. If the planet's spin had been different, so too would be the rhythm of our chemistry. It's as if Earth itself wrote its rotation into our DNA. The spin of the planet became the pulse of life. Each sunrise resets the clock. Each sunset reminds us that the universe turns, and we turn with it. Astronomers studying exoplanets often speak of the habitable zone, the region where liquid water can exist. But there is another quieter requirement. The rotational habitable zone, a planet may be at the right distance from its star, but if it spins too quickly or too slowly, its surface may be uninhabitable. Spin defines not only the passage of time, but the possibility of balance. The Earth's rotation, its axial tilt, and the pull of the moon combine to create stability that few worlds share. They prevent chaotic wobbling, keep the seasons steady, and preserve an environment mild enough for complexity to thrive. It is a partnership forged over 4.5 billion years, gravity, spin and chance, working in unison to create a planet that turns just right. So when you watch the horizon brighten each morning, remember that sunrise isn't merely the result of motion, it's the proof of balance, the fine-tuned spin that lets oceans breathe, clouds flow and hearts beat. Our world's gentle rotation is not trivial. It is the perfect imperfection that lets life endure. Life on Earth does not merely exist within time, it was built by it. From the first cell to the first consciousness, every creature has lived under the slow metronome of a turning world. The rotation of the Earth, its axial tilt, its orbit around the sun, these are not just motions of rock and gravity, they are the pulses that carved biology itself. When life began, the young planet spun faster. A day lasted only a few hours. The early oceans were in constant twilight, bathed in fierce ultraviolet light by day, and plunged into long freezing nights. Primitive cells learned to adapt to these extremes, developing molecular rhythms that told them when to protect themselves and when to divide. Those rhythms, simple chemical cycles at first, became the ancestors of what we now call circadian clocks. Even bacteria have them, tiny feedback loops of genes and proteins that oscillate with astonishing precision, roughly 24 hours, synchronized to the planet's rotation. In plants, these clocks tell leaves when to open, stems when to grow, flowers when to release pollen. In animals, they regulate sleep temperature and hormone cycles, and in humans, they orchestrate nearly every process in the body. From the firing of neurons to the repair of DNA, spin is the silent conductor behind this universal rhythm, but the influence of rotation doesn't stop at the daily scale. The axial tilt of Earth, about 23.5 degrees, creates seasons, periodic swings of sunlight and temperature that have sculpted evolution for hundreds of millions of years, the migrations of birds, the hibernation of mammals, the blooming of forests, and even the rise and fall of ice ages, all are consequences of a planet that spins not perfectly upright, but beautifully tilted. That imperfection gives the world diversity, forcing species to adapt, move, or perish. In the fossil record, we can see this pulse imprinted in stone. Coral skeletons layered like tree rings record the number of days in ancient years, showing that Earth's spin has been gradually slowing over time. Hundreds of millions of years ago, a year contained more than 400 days. That means shorter days, faster rotation, and faster biological rhythms. Evolution itself has adjusted its tempo to match the slowing heartbeat of the planet. The moon too plays its part. Its gravitational pull not only steadies Earth's tilt, but also stirs the tides that sculpted life's earliest forms. Every rise and fall of the sea was a whisper of time to the first organisms crawling onto land. In that rhythm of water and rotation, cells learned coordination, muscles evolved to move in waves, hearts to beat, lungs to pulse. Even our most intimate biological cycles are echoes of the ocean's tides, and through them of the moon's slow pull on Earth's spin. If evolution is the story of adaptation, then time is the ink, and spin is the hand that writes the cycles of day and night, of summer and winter, of tides and seasons are not mere scenery for life's drama. They are the script itself. Some scientists now believe that intelligence, the ability to anticipate and plan, arose from this same need to predict periodic change. Brains evolved as pattern detectors, and the first pattern every organism had to learn was the turning of the world, to know when to hunt, to hide, to rest, to sense that tomorrow will come. Consciousness may itself be a byproduct of rotation, the awareness of cycles within cycles. Our planet spins, and through that motion it teaches everything upon it. To move, to adapt, to remember, the pulse of Earth is not measured only by its rotation, but by the living systems that keep time with it. Every sunrise resets the clock of evolution. Every sunset prepares the next act of creation. And when you close your eyes tonight, you are in a sense returning to the same rhythm that began 4 billion years ago. The steady ancient turning of a world that spins just right. Every motion has a cost. Every spin, no matter how grand, eventually yields to time. The universe began in furious motion, space expanding faster than light, matter collapsing into stars, galaxies swirling into vast cosmic wheels. But energy spreads and order erodes. The same laws that gave rise to rotation also ensure that it cannot last forever. Angular momentum is conserved, but energy is not eternal in its usable form. Friction, radiation, gravitational tides all steal a little from the cosmic dance. Stars slow as they lose mass. Planets drift as they trade angular momentum with their moons. Galaxies bleed their spin into tidal tails. And on the largest scales, the expansion of space itself dilutes the rhythm of motion. Our own planet bears quiet witness to this slowing. Each century, the Earth's rotation lengthens by milliseconds, as tidal friction transfers angular momentum to the moon, pushing it a few centimeters farther away each year. 1 billion years from now, a day on Earth will last 30 hours, and the moon will hang smaller in the sky, a silent chronometer of our world's fading spin. The sun too is slowing. Its magnetic field drags against charged particles in the solar wind, bleeding angular momentum into interplanetary space. Astronomers call this process magnetic braking, and it acts as the aging mechanism of stars. By measuring a star's rotation, we can tell its age, a technique known as gyrochronology. The slower the spin, the older the star. Even the cosmos keeps time by how fast it turns. On galactic scales, collisions act as brakes. Each merger between galaxies redistributes their spin, converting ordered rotation into random stellar orbits. That's why elliptical galaxies, the ancient remnants of countless mergers, rotate far more slowly than youthful spirals. They are the retired dancers of the universe, their energy spent their grace replaced by stillness. But perhaps the greatest deceleration is written into the expansion of space itself as dark energy drives the cosmos apart. Gravitational interactions weaken, clusters drift farther from one another, and the exchange of angular momentum between them dwindles. The cosmic web, once taut with tension, is relaxing its strands, slackening under the pull of eternity. One day, far beyond human imagination, when the last stars fade and galaxies dim to embers, the universe will enter its quietest age. Rotation will persist, but faintly. Black holes turning in the dark, atoms vibrating with the last shreds of heat. Each motion slower than the one before, each revolution longer. As entropy completes its endless work, it's tempting to call this the death of motion. But in truth it is transformation. The energy that once built stars and galaxies will have diffused into the fine mist of space-time itself. Spin will not vanish, it will dissolve, its legacy preserved in the geometry of the universe. Everything that moves leaves an imprint, even when the last motion fades. The curvature it carved into space will remain. In that sense, nothing that ever turned will truly stop. The universe may slow, but it will never forget how to move. The stars will not shine forever. Even motion, beautiful and eternal as it seems, depends on fuel, and fuel runs out. For billions of years, nuclear fusion has powered the brilliance of the cosmos. Hydrogen fused into helium, helium into carbon and oxygen, forging the elements that built worlds and life. But each reaction drains a little of the energy that keeps the universe bright. And as the stars age, their spin, once fierce, once full of balance, begins to slow. When a star like the Sun exhausts its fuel, its outer layers drift away into space, leaving behind a dense glowing ember, a white dwarf, though no larger than Earth. It contains half the Sun's mass. It still spins, but sluggishly now, cooling for trillions of years until it becomes a black dwarf, a dark frozen cinder in the endless night. No more light, no more warmth, only the memory of motion fading into stillness. Massive stars end differently. Their cores collapse under gravity's weight, spinning faster and faster as they shrink, the skater's trick played on a cosmic scale. But the pressure becomes unbearable, and the atoms themselves shatter. Electrons and protons merge into neutrons, forming an object so dense that a teaspoon of it would outweigh a mountain. These are neutron stars, spheres barely 20 kilometers wide, spinning hundreds of times per second. Some flash like cosmic lighthouses, their magnetic poles sweeping beams of radiation through space. We call them pulsars. Each pulse is a heartbeat of a dead star still spinning, defying time itself. Even they will not last forever. As they radiate energy, their rotation slows, their beams fading into silence. Eventually gravity wins one final time, crushing what remains into a black hole, a region where even light cannot escape. Yet even there motion continues. Black holes spin too, dragging space and time around them in a whirlpool of gravity. Their rotation defines the shape of space-time itself, bending the universe into spirals that never unwind. The fastest known black holes can spin at over 99% the speed of light. Their rotational energy is so immense that it can power jets stretching across galaxies, beams of plasma millions of light years long. It's as though the universe stores its last reserves of motion in these silent engines, the final keepers of the cosmic dance. But even black holes are not immortal. According to Stephen Hawking's theory, they radiate energy through quantum effects, slowly, imperceptibly, shedding mass and angular momentum over unimaginable timescales. As they evaporate, their spin weakens. The last rotation in the universe may not belong to a galaxy or a star. but to a black hole evaporating in darkness, turning one final time before dissolving into light. By then the universe will be unrecognizable. No stars, no constellations, no warmth, only cold remnants drifting in a sea of black. Yet even in this quiet there is symmetry, a return to stillness that mirrors the beginning. The same physics that once ignited the stars will ensure their motion is never truly lost. Energy, spin and time, transformed, not destroyed. The lights will go out, but the echo of their turning will ripple through space-time forever. And perhaps if the universe could dream, it would remember not its brightness, but the feeling of having once been in motion. In the end, everything will slow, every star will fade, every atom will drift apart. The universe will not die in fire, but in silence. When the final black holes evaporate, their last whisper of Hawking radiation will vanish into the cosmic night. No light, no warmth, no gravity strong enough to shape motion again. Space will continue expanding, cold, vast and nearly empty, until distance itself becomes meaningless. But even then, spin will linger, not as motion but as memory. The curvature of space-time will still remember the vortices that once stirred it, every particle that ever turned, every galaxy that ever spun, will have left an imprint on the geometry of reality, a fossil record of movement in a universe that no longer moves. This is the heat death, the final equilibrium. Entropy has reached its maximum. There are no gradients left to drive change, no imbalance to fuel rotation. All temperature differences have evened out. All orbits have decayed. The cosmic symphony has played its last note, and silence has claimed the hall, and yet still the laws remain. Angular momentum is conserved, not destroyed, merely distributed, into scales so vast, so diffuse, that it no longer has meaning to us. Like a melody stretched beyond recognition, the rhythm of spin fades not by ending, but by spreading thin across infinity. Some physicists speculate that quantum fluctuations may still occur, tiny ripples in the vacuum, temporary twists of space and time. From one such fluctuation, a new universe might be born, its own expansion ignited by the same instability that once birthed ours. If that ever happens, the first motion of that new cosmos, the first rotation, will not be truly new. It will be an echo of this one. Maybe that is the secret of creation. There is no final stillness, only intervals between movements. Spin never dies, it only changes scale. And if consciousness somewhere someday could witness that final age, it would see not tragedy but continuity. Every cycle, every orbit, every turn was a note in a single unbroken pattern. From particles to planets, from atoms to galaxies, the universe spun itself into being, and now gracefully spins itself into rest. The last rotation may not be seen, or heard or measured, but it will happen, quietly, inevitably, beautifully, the final gesture of a cosmos that was born to turn. Nothing that ever moved is truly gone. Even when the universe falls silent, motion leaves behind a memory, woven into matter encoded in form, carved into the geometry of everything that remains. Every atom inside you remembers it. The iron in your blood was forged in the heart of a spinning star. The calcium in your bones was born in the collapse of a supernova, thrown into space by rotational fury. The very molecules of life, DNA, protein, cells, all carry the mark of motion. A twist, a helix, a rhythm. You are made of memory. You are made of spin. When you lift your hand, when you breathe, when a thought sparks in your brain, each action is a tiny echo of ancient movement, a continuation of the same cosmic turning that began 13.8 billion years ago. From the swirl of galaxies to the pulse of a neuron, there has never been stillness, only continuity. Perhaps that is why consciousness feels like motion. It flows, it turns upon itself, reflecting, looping, remembering. Every idea you form is a kind of rotation, matter thinking about its own movement. We are the universe's way of watching itself spin, and as we look outward, past our skies, our stars, our time, we find that everything still turns: electrons around nuclei, planets around stars, stars around galaxies, and galaxies around the unseen spine of dark matter, each level of existence built upon the last, each rotation a chapter in the story of becoming. The memory of motion is not stored in words or images. It is written in relationships, forces, balances, orbits. Even when the lights go out, that structure remains the eternal fingerprint of spin, pressed into space-time. And so, when the final particle stops moving, if such a thing could ever happen, perhaps the universe will remember, not as sound or sight, but as symmetry, the echo of all that once turned. Maybe that's what it means to exist at all. To move, to leave a trace, to become part of a larger rhythm. The cosmos began as pure motion, a swirl, a vibration, a breath, and every form that followed was built from that first act of turning. We are not separate from it. We are its continuation. When we look up at a spiral galaxy and feel something stir inside us, that quiet recognition, it's because something within us remembers, not in language, but in resonance. The universe spins, and so do we, and long after we are gone, long after stars and matter fade, that memory, the memory of motion, will remain. At the end of every journey, we arrive where we began, but see it for the first time. The universe began with motion, a flicker of imbalance, a single twist in a sea of nothingness. From that imperfection came direction, and from direction time itself, everything that followed, stars, atoms, life, thought, was born from that first act of turning. Now after billions of years, that motion is scattered into a trillion forms, some grand like galaxies swirling across the cosmic web, some small like electrons spinning silently in your body, yet everyone is connected, threads of a single spiral that never stopped unfolding. Perhaps this is what it means for the universe to remember, not in words, not in memory as we know it, but through persistence, the refusal of motion to end. Each orbit, each rotation, is a reminder that the story continues. We are the universe looking back at its own motion. Our curiosity, our longing to understand, is not separate from the laws that made us. It is those laws, matter thinking about motion, energy asking where it came from. And maybe that's why the question, why does everything spin, feels so profound, because hidden within it is another question. Why do we move, learn, search, create, turning endlessly toward meaning, as if trying to align with something larger than ourselves, in every galaxy, in every atom, in every heartbeat? The answer is the same, because spin is existence. Without it, there is no time, no balance, no being. It is the gesture that keeps reality from collapsing into silence. If you could look beyond the final stars, beyond the last black hole, into the darkness after time, perhaps you would still sense it, a pulse, a faint rhythm, the echo of the universe remembering itself. A whisper saying, I was motioned, I became matter, I dreamed of life, and through life I learned what I was. And maybe when our own consciousness dissolves back into that cosmic sea, the universe will spin once more, not as a beginning, but as a continuation. The circle will close, the silence will breathe, and in that breath, everything will turn again. Time seems so simple. The sun rises, the sun sets, days flow into nights. We build our calendars, our lives, and our history on that gentle rhythm, but behind this apparent simplicity there is a force invisible yet relentless that makes everything we know possible. That force is spin. The Earth is spinning right now. Every second it carries us through space at over 1,600 kilometers per hour at the equator. You don't feel it, but the movement is there, steady, silent, unstoppable. It is this spin that gives us our 24-hour day, our sunrise and sunset, our concept of now and later. If that spin were even slightly different, so would our time. Shorter days would race the sun across the sky. Longer ones would stretch the hours into a strange, unfamiliar rhythm. And if it stopped altogether, time as we know it would fracture. But this isn't just a story about our planet. From the smallest particles to the largest galaxies, everything in the cosmos spins. Stars spin, planets spin, black holes spin so fast they drag space and time itself along with them. Even the tiniest building blocks of matter, subatomic particles, carry something we call spin, a property so fundamental it shapes the universe at every scale. And here lies the mystery. Spin doesn't just mark the passage of time, it bends it, stretches it, sometimes almost stops it. This journey will take us from the familiar comfort of Earth's rotation to the dizzying edges of physics, where clocks slow down, where light itself bends, and where time is no longer a constant. We'll follow the thread of spin, not just as motion, but as a cosmic clock. Because the truth is this: time doesn't rule spin, spin rules time. At first glance, rotation seems simple. A child spinning top, a turning wheel, the hands of a clock. We see things spin every day. But what we don't see, what lies beneath that simple motion, is a rule the universe seems to follow everywhere. When something begins to move, it can slide, fall, or turn. And once it begins to turn, something remarkable happens. It doesn't want to stop. That's the essence of angular momentum, a quantity that measures how much spin a system carries. When nothing interferes, angular momentum is conserved. It stays, it persists. This is why a spinning top keeps spinning, why a figure skater speeds up when pulling their arms in, and why stars, planets, and galaxies keep turning long after their birth. But where does this spin come from in the first place? The answer lies in the earliest moments of the universe, when clouds of gas and dust collapsed under gravity to form stars and planets. They rarely collapsed perfectly still. Any tiny motion they had was amplified as they shrank, just like an ice skater spinning faster as they draw their arms closer. This simple principle forged spinning stars, swirling galaxies and planets like ours that never stop turning. This spin is not an accident. It's an inevitable byproduct of gravity and motion, and because it's conserved, it's astonishingly hard to erase. Even if you collided two spinning bodies, their angular momentum doesn't just vanish, it redistributes, often creating new rotations. On Earth, we see the results of that cosmic heritage. Our atmosphere circulates because of the planet's spin. Ocean currents form patterns around it. Weather systems swirl into cyclones and hurricanes because of something called the Coriolis effect, a direct child of Earth's rotation. But Earth is just one example in a cosmic sea of spinning worlds. From the tiniest asteroid to the largest supermassive black hole, rotation is everywhere. It's one of the most universal behaviors in the entire cosmos, and it's the key to understanding why time doesn't flow the same everywhere. Because as rotation grows stronger, time itself begins to bend. If you spin something fast enough, you don't just create motion, you begin to bend time itself. This is one of the most counterintuitive truths in modern physics. The faster an object moves, the slower time flows for it. This isn't science fiction. It's a direct consequence of special relativity, first described by Albert Einstein more than a century ago, and rotation is one of the purest ways to experience this effect. Imagine two identical clocks. One remains on the ground perfectly still. The other is strapped to a rotating ring, spinning at incredible speed. According to relativity, the spinning clock experiences time more slowly. To the clock itself, everything seems normal, but when the two are compared afterward, the spinning one will have ticked fewer seconds. This is not a thought experiment. It's been measured in experiments with atomic clocks placed on aircraft satellites, and even at different latitudes on Earth. Physicists have seen tiny but measurable differences Clocks closer to the equator moving faster due to Earth's rotation tick just a fraction slower than those near the poles. The difference is small, but it's real. Why? Because spinning is a form of velocity. Every point on a rotating object moves through space. The faster the spin, the greater the velocity at the surface. And as velocity approaches the speed of light, time dilation grows extreme. For example, if the Earth were to spin much faster, people at the equator would age imperceptibly slower than those closer to the poles. If you spun something close to light speed, a single day for it could equal years for the outside world. This phenomenon isn't just theoretical, it's essential for technologies like Global Positioning System. GPS satellites orbit Earth at high speeds, so their onboard clocks tick at a slightly different rate than clocks on the ground. Without compensating for relativity, GPS would drift by kilometers in just a day. When things spin fast, they carry time with them at a different pace. Every rotation isn't just movement through space, it's a step into a different timeline. And Earth itself is part of that strange ballet. Every second as the planet turns beneath our feet, our clocks are already experiencing a microscopic but real shift in time. A reminder that even here, we're living inside the fabric of relativity. We like to think of time as something universal. A second is a second everywhere. A minute is always 60 ticks. But that's only an illusion. On a spinning world like Earth, time doesn't flow evenly. Every point on the planet is moving through space at a different speed. At the equator, Earth spins fastest more than 1,600 kilometers per hour. Near the poles, the velocity drops towards zero. This difference might feel meaningless to us, but to time itself it matters. According to special relativity, the faster an object moves, the more slowly its time passes relative to a slower frame. This means a clock placed at the equator moving through space faster because of Earth's rotation ticks more slowly than a clock placed at the pole. The difference is tiny billionths of a second each day, but it's measurable. In fact, scientists have done exactly that. With atomic clocks so precise they can detect changes smaller than a trillionth of a second. They found that two clocks, one at the equator, one near the pole, drift apart ever so slightly over time. The equatorial clock runs a bit slower, not because its mechanism is broken, but because it exists in a different slice of space-time. It gets stranger. Because Earth is not just spinning, it's also not a perfect sphere. It bulges at the equator due to its rotation. This changes gravitational potential slightly, and under general relativity, gravity also affects time. Stronger gravity slows time, weaker gravity lets it run faster. So both velocity and gravitational differences are working together at the equator, and they both pull time slightly backward. This isn't some hidden trick of physics. It's happening beneath our feet right now. If you lived your entire life at sea level on the equator, you would age just a few milliseconds less than someone who lived the same life at the poles. You'd never feel it, but the universe would keep the score. These tiny time differences are so real that technologies like GPS must correct for them. Satellites orbiting Earth don't just deal with speed, they also feel weaker gravity. Their clocks run faster than ours, and engineers must continuously adjust for relativity to keep your phone's navigation accurate. Without those corrections, your location could be off by kilometers within a single day. On a spinning world, there's no single universal clock. Every latitude, every altitude, every orbit has its own timeline. Earth's rotation is carving invisible layers of time across the planet like rings in a tree. We just don't notice, because we're spinning with it. And this is only the beginning. The stronger the spin, the more time bends. On Earth the effect is small, but out in the cosmos where rotation reaches unimaginable speeds, time doesn't just drift, it warps. Up to now we've looked at how rotation affects time through speed, but nature hides something far stranger. When something massive spins, it doesn't just move through space and time, it drags them along. This phenomenon is known as frame dragging, a subtle but extraordinary prediction of general relativity. According to Einstein's theory, space and time are not passive backgrounds. They behave like a fabric that can bend, twist, and flow around massive objects. And if that object spins fast enough, it pulls this fabric into a slow cosmic whirlpool. Imagine placing a marble on a trampoline. The fabric bends and smaller marbles roll toward the heavy one. Now spin that heavy marble. The fabric doesn't just dip anymore, it starts to twist. Nearby marbles are no longer moving in straight lines. They're caught in a slow spiral dragged by the fabric itself. That's frame dragging. This isn't just theory on paper. In 2004, NASA launched a remarkable experiment, Gravity Probe B. 4 ultra-precise gyroscopes were placed in orbit around Earth to detect whether our spinning planet drags space-time with it. After years of analysis, the results were clear. Yes, Earth does drag space-time. The effect is incredibly small, but measurable. Our planet doesn't just move through time, it tugs time along for the ride. Now imagine a more extreme example. A rapidly spinning neutron star packing the mass of our Sun into a sphere barely 20 kilometers wide, twists space-time so powerfully that nearby matter spirals around it like water down a drain. And at the ultimate extreme, a rotating black hole. The effect becomes violent. Their frame dragging is so intense that nothing can remain still. Space and time are whipped around like ribbons in a storm. This means something extraordinary. If you were hovering near a massive, rapidly rotating object, your sense of time would not be your own, even if you weren't moving at all. Space-time itself would be moving around you. Earth gives us just a faint whisper of this effect, but across the cosmos frame dragging sculpts entire systems. It shapes the disks of accreting black holes, spins up relativistic jets that pierce light years of space, and determines how galaxies evolve. Spin doesn't just happen in space-time. Spin reshapes space-time. Every world in the universe has its own rhythm. Some turn slowly, drifting through long, lazy days. Others spin so fast that a single day flashes by in the blink of an eye. And hidden within those rotations is a quiet secret. Each of these spinning worlds ticks time differently. Take Earth, our familiar reference point. A day lasts 24 hours because of its moderate rotation speed. At the equator, this gives us a surface velocity of about 1,670 kilometers per hour. That's enough to bend time ever so slightly, but not enough for us to notice. The effect is microscopic, a whisper. But out among the stars, this whisper can turn into a roar. Look at Jupiter. It's more than 11 times Earth's diameter, but spins in less than 10 hours. Its equator hurtles through space at nearly 45,000 kilometers per hour. That speed is so extreme it flattens the planet into an oblate shape bulging at the equator. It also warps time more noticeably. Clocks on Jupiter's equator would tick slightly slower than those on its poles or far away in deep space. Jupiter doesn't just rotate, it drags time with it. And then there are the stars. Many of them spin far faster than planets. Young stars still collapsing from swirling clouds of gas often rotate hundreds of times faster than Earth. Some massive stars spin so violently that they begin to fling matter away from their equators, forming luminous disks that stretch across space. In their intense gravitational fields, time slows more than it does anywhere near a planet. But the most dramatic cases are not stars or planets. They are stellar remnants, neutron stars. When a massive star dies, its core collapses into an object barely 20 kilometers wide, but still holding more mass than our Sun. Conservation of angular momentum forces the remnant to spin at breathtaking speed. Some neutron stars, known as pulsars, rotate hundreds of times per second. Their equators move at a significant fraction of the speed of light. At that speed, relativity is no longer subtle. Time dilation becomes dominant. To an observer standing on such a star's surface, if they could survive the crushing gravity, time would pass dramatically slower than for someone watching from far away. A second near the star might equal many seconds beyond it. Spin doesn't just shape the appearance of these objects, it changes their timeline. Two clocks side by side in deep space will tick differently if one is dragged into a spinning gravitational field. This isn't science fiction, it's physics, and it's measurable. The universe is full of cosmic clocks. Every rotation marks a beat. Every beat carries a signature in space-time. And as the spin grows stronger, the clockwork of the cosmos slows down. There is a place in the universe where spin reaches its ultimate expression, where gravity is so strong and rotation so extreme that space and time themselves become trapped in a cosmic whirlpool. These are Kerr black holes, spinning black holes. Unlike an ordinary non-rotating black hole, a Kerr black hole doesn't simply sit in space. It drags space-time around with it at incredible speeds. The faster it spins, the more violently it twists the fabric of reality. This isn't just a metaphor, it's a precise prediction of general relativity. These objects are described mathematically by Kerr metric, a solution found in 1963 by Roy Kerr. Around a spinning black hole is a region called the ergosphere. It isn't the event horizon, but a layer outside it, a place where space-time is dragged around so fast that no object can remain still. Even light itself is forced to orbit in the direction of the spin. Inside the ergosphere, time behaves differently. An observer hovering there, if they could somehow survive the crushing tidal forces, would experience time moving much more slowly than someone far away. Their clock would tick slower not because of speed alone, but because space-time itself has been twisted by rotation. And as the spin approaches its theoretical limit, the distortion becomes so intense that the flow of time near the event horizon effectively slows to a crawl. From the outside, an object falling toward a rapidly spinning black hole seems to freeze in time, but from its own perspective, time flows normally. This strange duality is one of the most breathtaking predictions of relativity. Kerr black holes also offer something unique. Because of their spin, they allow energy extraction from their ergospheres, a phenomenon predicted by Roger Penrose. In principle, a spacecraft could dive into the ergosphere, steal some of the black hole's rotational energy and escape with more energy than it entered with. This isn't fantasy, it's mathematically sound physics. These objects may be common in the universe. Many supermassive black holes at the centres of galaxies, including Sagittarius A at the heart of the Milky Way, are believed to spin at extraordinary speeds. Their spin powers vast, collimated jets that shoot particles across intergalactic space at nearly the speed of light. They shape galaxies, regulate star formation, and define the cosmic environment far beyond their event horizons. When you approach a Kerr black hole, you don't just fall inward. You fall through time itself into a landscape where time is stretched, slowed, and twisted around a cosmic vortex. Spin here isn't a background detail, it's the master of time. In the calm space between stars, space-time flows smoothly like a quiet river. But near a spinning monster, like a Kerr black hole, that river doesn't just bend, it swirls. Spin doesn't only shape the flow of time, it entwines time and space into a single inescapable current. In a region near the ergosphere, standing still is no longer an option. Even if you fire engines in the opposite direction, space-time itself is being dragged around so forcefully that you must move with it. Here, motion isn't a choice, it's the law of the universe. Physicists call this phenomenon the co-rotation of space-time. Imagine a leaf on a whirlpool. No matter how hard it tries to resist, the spinning water carries it along. Replace water with the fabric of reality, and you have the effect of a spinning black hole on everything nearby. Even on time, this is not just poetic imagery. Equations derived from the Kerr metric show that time and space trade roles in the near-horizon region. The direction of time becomes entwined with the direction of rotation. You can't move freely against the spin because forward in time itself is locked to it. This is why near such an object a clock behaves like no clock anywhere else. The more you try to fight the spin, the slower your clock runs. If you align with the spin, you can survive closer to the horizon without being torn apart, because you're moving with time itself. In the wrong direction, you're moving against time, and the price for that is infinite energy. This strange geometry isn't limited to black holes alone. Spinning neutron stars or even rapidly rotating white dwarfs also twist space-time, though less dramatically. Their spin sets the local rhythm of time. A second far away doesn't equal a second near their surface. These differences may seem tiny, but in astrophysical processes they shape how matter falls, how energy flows, and how light escapes. What's extraordinary is this: spin can create pathways through space-time that wouldn't exist otherwise. Some theoretical models even suggest that under the right conditions, a rapidly spinning black hole could act like a cosmic tunnel, not because it punches a hole through space, but because it twists time so violently that new geometries emerge. In these regions, past, present, and future don't behave like they do here. They blur. Spin doesn't just slow time down, it dictates what time even means. The farther we travel from our slow-spinning Earth, the more we see this truth. Spin isn't just another property of matter, it's a cosmic architect, carving the structure of space and time itself. When we look up at the night sky, we're not just seeing stars. We're looking into the arms of a vast rotating structure, a cosmic pinwheel so large it defies imagination. Our home, the Milky Way, is not still. It spins. The entire galaxy, 100,000 light-years across, rotates like an enormous cosmic disk. Billions of stars, countless clouds of gas and dust, all orbiting around a central gravitational anchor, and at the heart of this grand motion, a supermassive black hole, Sagittarius A. Every star, including our Sun, takes part in this vast choreography. The solar system orbits the galactic center at nearly 800,000 kilometers per hour. One full revolution takes about 230 million years. This colossal spin is one of the great engines of cosmic structure. But why does the galaxy spin at all? The answer is written into the universe's birth. After the Big Bang, matter wasn't distributed perfectly evenly. Tiny fluctuations grew under gravity, pulling gas together into clusters, and as those early clouds collapsed, any slight twist, no matter how small, was amplified, just like a figure skater pulling their arms inward. Entire proto-galaxies spun faster as they shrank. What began as a whisper of motion became a galactic storm of rotation. This spin isn't just a quirk of galactic evolution, it's essential to how galaxies hold their shape. Without rotation, the disk of the Milky Way would collapse under its own gravity. The centrifugal effect of spin counterbalances the inward pull, allowing spiral arms to form and stars to orbit stably for billions of years. But rotation on this scale doesn't just shape space, it shapes time too. Every star moving around the galactic center experiences a different flow of time depending on its velocity and gravitational position. Stars closer to the center move faster and live inside a deeper gravitational well, so their clocks tick more slowly compared to stars farther out. These differences are microscopic compared to black holes, but over cosmic timescales they accumulate. Our Sun, out in one of the quieter suburbs of the Milky Way, is part of this grand temporal gradient. We don't feel it, but our clock is not in perfect sync with a clock orbiting closer to the galactic core. And it doesn't stop there. Galaxies themselves interact through their spins. When two galaxies collide, their angular momentum doesn't vanish. It combines, reshapes, twists. The resulting galaxy carries the memory of their past rotations in its stars, in its shape. And in its timeline, the Milky Way isn't unique. Virtually all galaxies in the observable universe rotate. Their spins are cosmic fingerprints, echoes of their origins, and the invisible hands that stretch time across unimaginable distances. Spin gives galaxies their structure, but it also sets the tempo of the universe at that scale. a deep slow heartbeat written in stars. Spin isn't just something galaxies do, it's one of the master builders of the universe, from the smallest clusters of matter to the largest cosmic webs. Spin shapes structure, it determines where stars are born, how galaxies evolve, and how the flow of time itself is stretched across space. When matter gathers under gravity, it almost never collapses straight down. Even a whisper of rotation in the beginning becomes enormous as the cloud contracts. This is conservation of angular momentum in action, the same principle that keeps a spinning top upright, but now acting on entire galaxies. This rotation sets up a balance. Gravity pulls inward, while centrifugal force pushes outward. Together they sculpt flat rotating disks, spiral galaxies like the Milky Way, owe their iconic shape to this cosmic tug-of-war. Without spin, they would be shapeless clusters of stars collapsing into dense knots. With spin, they become stable, organized structures that can last for billions of years. But this isn't just about geometry, it's about time. Spin influences the distribution of gravitational wells across a galaxy. In regions of faster rotation, matter spreads out more, softening gravity's grip. In slower regions, gravity dominates, pulling stars inward. This creates gradients in both space and time. Clocks near the galactic center tick slightly slower than clocks in the outer arms. In a sense, the galaxy is like a vast invisible time machine, not one that lets you travel through eras, but one that stretches the flow of time across its structure. Different parts of the galaxy live in subtly different timelines, all synchronized to the beat of its rotation. The influence of spin extends even further, to the filaments and clusters that make up the large-scale structure of the universe. Observations suggest that galaxies are not oriented randomly. Their spins often align with the cosmic web, as if the rotation of entire galaxies were choreographed by a larger hand. Spin is not just born from structure, it builds structure. Over cosmic timescales, these spinning systems exchange angular momentum. Galaxies merge, clusters form. Each interaction passes spin along like a baton in an endless relay, and through it all time continues to stretch, bend and flow according to the shape of those rotations. The universe is not static, it's a dance of spin, a choreography of gravity and motion. Spin sets the stage, defines the rhythm and shapes the timeline. Until now we've been exploring spin in the vastness of space, planets, stars, black holes and galaxies. But spin doesn't belong only to the cosmos, it lives in the very fabric of matter itself. In the world of quantum mechanics, spin is one of the most fundamental properties of particles, as basic as mass charge or energy. But here the word spin doesn't mean what it does in classical physics. An electron doesn't physically rotate like a tiny planet. Its spin is an intrinsic property, a kind of built-in angular momentum that defines how it behaves in the quantum world. This quantum spin determines how particles interact with magnetic fields, how they align and how they obey the deep symmetries of nature. For example, the spin of electrons gives rise to magnetism, one of the most familiar forces in our daily lives. The electronics that run our modern world are at their core, machines built on the manipulation of quantum spin. But there's something even more profound. Spin is directly tied to the structure of time itself at microscopic scales. Every fundamental particle belongs to a class determined by its spin. Fermions with half-integer spins like 1, 2, 32. These make up matter. Electrons, protons, neutrons, bosons with integer spins like 0, 1 or 2, these carry forces. Photons, gluons, gravitons, hypothetical. This simple distinction decides whether particles obey the Pauli exclusion principle, the rule that builds the structure of atoms, the periodic table, and everything solid in the universe. In other words, spin decides how matter stacks up in time and space. Even more intriguingly, quantum spin isn't symmetrical. Nature has a subtle bias, a preference for certain-handedness. This is called chirality. For some interactions, like the weak interaction, Only particles of one-handedness participate. This tiny asymmetry is believed to be part of the reason our universe looks the way it does. Matter won over antimatter in the early moments after the Big Bang. And time too may owe its arrow to this asymmetry. If the universe were perfectly symmetric, if spin pointed equally in both directions, the balance between past and future might not exist as we know it, but spin's slight tilt, its quiet bias, may be one of the first choices the cosmos ever made. Spin at the quantum level isn't just a detail of physics, it's a foundation. It determines how particles behave, how forces act, how matter builds structure, and perhaps even why time flows forward, from the edge of galaxies to the heart of atoms. Spin tells the same story just in different languages, and at the smaller scales, it may be writing the first lines of time itself. Time has a direction. We wake up, grow older, watch the world change and never go back. We can't rewind the sunrise. We can't unshatter glass. Everything in nature seems to obey this arrow of time, an invisible current that pushes the universe forward. But why does time flow in only one direction? The laws of physics, at least most of them, are symmetric. They work just as well going forward as they do backward. Yet the universe doesn't behave symmetrically, and one of the deep clues to this mystery lies in spin. At the quantum level, particles don't just exist, they have orientation. Spin gives them handedness or chirality, and nature in a subtle but fundamental way doesn't treat both hands equally. In the weak interaction, which governs processes like radioactive decay, particles with one-handedness behave differently from their mirror images. It's as if the universe quietly prefers one direction over another. This is more than a mathematical quirk. It means that the building blocks of reality encode a symmetry into their behavior. When particles decay, their spins and emission directions don't form mirror-perfect patterns. This built-in bias can be traced back to the earliest instance after the Big Bang, when matter and antimatter should have annihilated each other completely, but they didn't. A tiny imbalance, possibly tied to the orientation of spin, allowed matter to survive, and with it, everything we know. Spin's role here is subtle but powerful. It doesn't create time's arrow, but it tilts the stage on which the arrow is drawn. Imagine a perfectly balanced universe, where every spin has an equal mirror opposite. Such a cosmos might have had no clear distinction between past and future, no preferred direction for entropy to rise. But in our universe, asymmetry in spin gives a faint initial push, and entropy, the disorder that grows with time, follows that push, turning it into a one-way current. Even today, that preference shows itself in countless ways. Neutrinos only interact with left-handed spin. Their mirror twins, right-handed neutrinos, are nowhere to be found. This isn't random. It's baked into the laws of nature. This is why physicists suspect that spin and time may be more deeply connected than we currently understand. The arrow of time might not just be an emergent property of thermodynamics, it might also be a fingerprint of the universe's spin bias, etched into reality at its most fundamental level. The flow of time is not just something we feel, it might be something the particles themselves enforce. Change the spin, change the day. If Earth turned faster, the sun would sprint across the sky mornings and evenings, compressed into quicksilver flashes. The equator would race ahead, the planet swelling a little more at its waist, and your weight there would ease by a whisper, not enough to notice with a bathroom scale, but enough for physics to keep the score. Atomic clocks would hear it first. Time at low latitudes slipping a fraction behind that tiny relativistic lag, growing with every extra turn per day. Air would try to keep up with rock. Jet streams would tighten, then snap into new lanes. The invisible hand that steers cyclones, the Coriolis effect, would press harder, sharpening curves into tighter spirals. Storms would spin up faster, travel farther, and carry more angular momentum in their bones. The tropics would breathe in shorter, louder gasps. The mid-latitudes would inherit a livelier parade of fronts. Seas would heap a little higher toward the equator as the bulge deepened, nudging shorelines, retuning tides and coastal currents. And beneath the weather biology would protest. Our bodies are written to a 24-hour rhythm. Hormones cresting and falling temperature drifting, neurons dimming and brightening like a lighthouse lens. Halve the day, and you don't just rearrange calendars, you tug at the gears inside the skull. Sleep fragments. Hunger arrives offbeat. Work school conversation, all of it tries to march while the drumline changes tempo. We could fight it with shutters and LEDs, with shift schedules and pharmacology. But the sky would keep conducting and life would learn the new key the hard way. Slow the planet and the transformation runs in the other direction. The sun lingers. Noon does not blaze. It loiters, pouring steady heat into land and ocean for long unblinking hours. Night is not a pause. It is a season. With more time to bake and more time to cool, the swing between day and night grows wide. Winds weaken because rotation gives them less twist. But the thermal contrasts they must bridge become immense. Circulation reorganizes. Instead of 3 stacked cells in each hemisphere, vast Hadley cells swell poleward, hauling heat in long, tall loops. Monsoons stretch into epics. Deserts expand under drawn-out suns, frost bites deeper under extended stars. Hurricanes lose some of their familiar spin, yet heat has patience, and it finds other paths to violence. Slow-moving, sprawling storms that drown coasts simply by refusing to leave. The seas answer with their own inertia. Tides slip out of sync with human habit as the day lengthens and resonances shift. Coastal ecosystems that once timed their lives to a reliable cadence now misfire. Fisheries wander. Bloom and spawn calendars tear loose. On land, agriculture meets a different clock. Crops bred to open and close their stomata on a tight schedule now face afternoons that last a lifetime and nights that overstay. Farmers can chase shade with fabric and water with pipes, but the sky does not blink and the soil remembers. In both futures the same truth speaks. Time still obeys the laws we trust, but our experience of it bends with the planet's turn. Faster spin means stronger relativistic drag on clocks at low latitudes. Fiercer curvature in the pathways of air, more kinetic energy stored in the day's machinery. Slower spin means gentler curves, but harsher contrasts. A climate ruled less by swirl than by standoff, with heat and cold staring at each other across a longer divide. And threaded through both is the human problem, entrainment. We do not simply watch the day, we entrain to it. Cells keep molecular time. Organs keep sectional time, communities keep civil time. Change the metronome and the orchestra stumbles. Then it retunes or it breaks. None of this is apocalypse. It is a reminder. Spin is not background decoration. It is the quiet engineer of habitability and the custodian of our inner clocks. The planet's rotation sets the length of a story we repeat every sunrise. Sleep, wake, work, eat, speak, dream. Speed that story up and life breathes in quick, shallow phrases. Slow it down and life speaks in long, heavy sentences. Either way, the punctuation changes. Shorelines redraw themselves by millimeters and then by miles. Winds learn new corridors. Cultures invent new calendars. Science rewrites the algorithms that keep satellites honest and cities synchronized. And through every adjustment, the lesson stays simple enough to whisper to a child. The world turns and time turns with it. If the beat quickens, we hurry. If the beat slows, we wait. The melody seasons, weather biology, memory is arranged around that beat. Change the beat and everything you can name changes its phrasing. Everything we've explored comes down to this. Spin is not just motion. It is the quiet metronome of the cosmos. From the slow turning of planets to the blazing fury of black holes, from the graceful swirl of galaxies to the invisible handedness of subatomic particles, spin writes time into the structure of reality. When a planet spins, it sets the rhythm for every heartbeat, every sunrise, every story told beneath its sky. When a star spins, it sculpts gravity and light pulling on space-time like a great conductor guiding an orchestra. When a galaxy spins, it shapes how entire clusters of stars breathe and evolve. And when a black hole spins, it reaches into the fabric of existence itself, dragging time into its vortex. But spin also lives in places we cannot see. Deep inside atoms, the spin of particles decides how matter stacks together, how forces behave, how the arrow of time leans in one direction instead of the other. It is written into every decay, every collision, every whisper of the quantum world. This is why time is not something separate from motion. Time is woven into motion and spin is the thread. Every clock, whether mechanical or atomic, is nothing more than a way to count cycles. A second is a number of oscillations. A day is a single turn of a world. A year is an orbit around a star. Time is built on motion, and motion almost always means spin. If you could somehow remove every rotation from the universe, what would remain? No planets turning, no stars twisting, no galaxies swirling, no electrons spinning in their quiet quantum rhythm. Perhaps time itself would lose its heartbeat. It might still exist as a dimension, but not as an experience. The flow we know would fall silent. Spin doesn't just shape time, it sustains it. It keeps the universe from being a still timeless void. It gives us mornings and nights, beginnings and endings, memory and change. It is the cosmic clock that never stops ticking. Not on a wrist, not on a wall, but in the fabric of existence itself. When you stand on Earth and feel nothing beneath your feet, remember this. The world is spinning, the stars are spinning, the atoms in your blood are spinning. And with every turn, large or small, the universe whispers the same message: time moves because everything does. Stand outside on a still night, and it feels as if the world isn't moving at all. The air is quiet. The stars look frozen, but nothing is still. Not the ground beneath your feet, not the galaxy above your head, not even the smallest piece of matter that makes up your body. Earth turns, the moon orbits. The sun spins around the heart of the galaxy. Every star in that spiral carries its own angular momentum. Every galaxy is part of a larger cosmic rotation. Even at the subatomic scale, the particles you're built from hum with spin, silent, ceaseless, absolute. The passage of time isn't floating somewhere outside of all this. It's emerging from it. The rhythm of rotation from the quantum up to the cosmic is the true clockwork of the universe. Every cycle, a planet's day, a star's spin, a photon's wave becomes a heartbeat that defines how time unfolds. We build clocks out of gears, out of quartz, out of cesium atoms, but all of those are merely echoes of deeper, older clocks that the universe built long before us. Time as we live it is carved out of motion. And motion itself is written in the language of spin. When we talk about time, we're really talking about turning, about the unseen pulse beneath everything, about a universe that never rests. The cosmos doesn't tick, it turns, and with every turn it carries us forward whether we notice or not. Spin is the secret clock, the one we never built, the one we can't stop, the one that keeps the universe alive.